Hello there, welcome back to Petrophysics Rocks. It's been a while since my last upload, I do apologise. Did you miss me? I've been busy being retired as it happens. I've been over in Germany for a couple of weeks visiting some car factories, driving some autobahns and stuff, which is quite enjoyable. But since I've been back, I've been working on the next presentation. This is Thinbed log analysis from conventional logs. It's an old reservoir that I used to work on back in the day in the early 90s. You know, sometimes you think your young self, I wish I could do that again, have another go at that. Well, I've taken this opportunity to revisit something I was working on back in the early 90s, the Nelson field, the Nelson oil field, and we had a thin bed problem. You see some invisible rocks, difficult to see because they're so thinly bedded below the resolution of our logging tools. And we used a technique back then which was cutting edge at the time. And I'm revisiting it now with the benefit of 30 years more hindsight and experience, and see if I can bring together some expertise and apply it to some old work that I did. And did it improve it? Well, probably not, actually. But it was quite good to revisit some of the stuff we did and think, actually, that kind of stands the test of time. Some of the conclusions are still pretty similar. There's a little bit more work that's come up with it. And in fact, that's part of the problem I've had been putting this presentation together, reminiscing about the old days, good old days. You go back and you think, oh, what about this? Oh, yeah, I remember that. What's the problem with that? So I got kind of sidetracked down a few rabbit holes. And there's a bit of further work that I've suggested that I might do over the next 35 years. But I thought, no, I've got to stop it now. Let's get this YouTube video up. My audience, my ever-growing audience is waiting. So please do give me a like and subscribe if you like it. And if you don't like it, give it a thumbs down. Any sort of interaction apparently kind of works with the YouTube algorithm. As we grow the channel, as I grow the channel for you guys, I don't know what I'm still trying to get these presentations down to a more manageable size. But as you'll see from the thumbnail, the duration, I've failed again. I drift on and on a little bit, but hopefully those of you who are considering giving this methodology a try, I've given you enough information that you should be able to do it, even with whatever software you're using. And there's a couple of little tips in there as well to help you along the way. So hopefully you'll appreciate it. As I say, give me a like and subscribe, comment down below, all that good stuff. Now let's go and start the new presentation. As I say, difficult to see some of these thin beds, but let's see how we get on. Okay? Right. Thanks a lot for your attention. See you next time. Hello there. Welcome to my latest presentation. This one's called Thin Bed Analysis from Conventional Logs. Sometimes in petrophysics we have issues with very thinly bedded or finely laminated rocks, and to evaluate those when they're below the resolution of our normal logging measurements, we have to employ some special techniques. And one of the things I'm going to share with you now is how we can tackle these kind of problems with conventional logs without necessarily reverting to expensive high-resolution imaging logs, for example. We're going to be using an example reservoir that I worked on about 35 years ago, and the Nelson field, which I was involved with the development well logging back in the early 90s, and to see whether I can use some of the experience I've gained over the last 35 years to go back and help my younger self tackle these kind of problems. Now, I don't know whether I'm going to succeed, but nevertheless, it's often nice to go back and revisit old things and think, how many times have you wished, if only I could have done that again? Well, here I'm taking this opportunity to do just that. Go back and see if I can recreate what I recall us doing in the early 90s, and using this conventional logging suite to evaluate a thin bed problem. Okay, so I'm going to talk about various things in this presentation. I'm going to talk about repairing some logs in bad hole, some of the use of core photographs and core information that we've got. I will touch on some of the dip meter, the high resolution, I say imaging logs, but of the early 90s in oil-based mud, they were a bit limited. But nevertheless, I'll have a quick look at them, just more in terms of QCing this methodology and cross-checking, if you like, to see whether what we've done actually makes sense from a high resolution logging point of view. But as I say, the bulk of this presentation is going to be about conventional log interpretation. I will, of course, discuss the methodology, outline the methodology, and then show you, as I usually do, we'll walk through an interpretation. You can see exactly how it's applied, and hopefully give yourself some ideas about how you could apply such techniques, even if you don't have the exact same software that I do. This pretty basic fundamental maths that you can apply in your own world, and I'm sure if you sit down with a cup of coffee and think about it appropriately, you'll get on fine with whatever software you're using. But anyway, as I like to start out these presentations every time, I like to give you a bit of a background about myself. For those of you who don't know me, I'm Graham Davis. I started out in the mid-80s at a small UK independent company called Enterprise Oil. Well, actually, it's not that small. It was a large UK independent at the time. Then I jumped ship from there before it became popular, and joined Shell voluntarily before the rest of my colleagues were later taken over by Shell. And I spent some time out in Oman with Shell, and then I came back to the North Sea with BP, another company you might have heard of. And then I joined the company that you probably haven't heard of, Canadian Natural Resources, again in the North Sea. And then the last few years I spent at Premier Oil, and then which became Harbour Energy. I've been involved in various things. I chaired the DevEx conference a couple of times. It's a subsurface conference in Aberdeen, so I've been involved in multidisciplinary work with our colleagues at Reservoir engineers and geologists. And I was local president of the local SPWA, Society of Professional Petrophysicists and Well Log Analysts. That's right. Yeah, I was president of that society a couple of times as well. And obviously I've been involved in online training with my website and my YouTube channel, which is now really taking off. I've got a few hundred subscribers now, so hopefully this will add to the list, and hopefully it won't put you off pressing the subscribe button down below and joining me on our journey of petrophysical exploration. So what are we going to talk about today? This is where I've worked around the world, various places, various basins that I've worked. I've lived in Oman and Aberdeen, exotic, and worked in various basins around the world. But this presentation is going to be one from the UK, and more specifically the North Sea in the UK. And this particular location here is the Nelson platform. And this is Nelson. Obviously, back in the early 90s, we didn't have such sophisticated graphics and logo consultants. Somebody, I think, won the prize for can you design a Nelson logo. So I think one of the geologists earned the prize for that. But obviously, this is the platform, which is there still, I think. Although they've just announced that they're going to. Excuse me, just going to press that button there a bit. They just announced that they're going to abandon it shortly. So I don't know how much longer it's going to be there. But obviously, most of the interesting stuff, as far as I'm concerned, obviously, is down below the surface, the subsurface, below the seabed. And this is the first development well, N1, the Nelson first well. And it was done, 27th of December 1991. Obviously 1991 was a good year for well logging, and platform development drilling, and obviously also Elton John lookalike competitions, obviously. So anyway, if we take a look bit more detail about the logs that we obtained in N1, well, we didn't do a particularly good job, it seems. We got hung up here. So normally when you drill the hole, you drill it in hole sections down through the reservoir. And obviously in this particular hole section, we got hung up. We couldn't get the logs down below a certain depth. So then we had to set pipe and drill on. And then we got another bit of scrappy log down here in the reservoir section in the 8.5-inch hole. And then I think we attempted to record some logs through casing, through the metal pipe that we set, sonic logs, and catch it through the casing to join up with the previous hole section. But this is the interval of interest down here. But overall, a pretty scrappy set of logs for the first platform well. So how can we construct an interesting YouTube presentation out of that? Well, trust me, I'm going to have a go at trying to make something interesting out of it anyway. So this is the main interval of interest, and even in this particular hole section, you see that we got hung up as well. We didn't get complete log coverage. Back in these days, we often used to run the resistivity and sonic logs separately from the density neutron, the radioactive tools. This was basically a common practice at the time. You didn't know what the hole conditions were going to be like, so you would commit to running the gamma ray, resistivity and sonic log. These are just simple mechanical, electronical logs. You can run them in, and once you've made that log, you're pretty sure that the hole conditions are good. There's not a sticking hole. It's pretty safe to then go in with the density and neutron logs, which have radioactive sources on them. And so they beam radiation into the formation, and you measure the stuff that bounces back. If you refer back to my Petrophysics for Dummies seminar, obviously you'll know all about that. You'll be an expert at that. But in this particular case, we've obviously got the first logs down, and then when we came in to run with the density neutron logs, unfortunately we couldn't get down below here. So, and overall, it's a pretty scrappy set of logs here. This is the compressional shear velocities. That's the compressional sonic logs. Those are the ones that pulse through, send a sonic wave through the well bore, through the borehole formation in a compressional fashion. And then this is the shear log here, which is a bit of a slower traveling wave. It kind of moves, it wobbles the rock from side to side, and you can see, or maybe you'll notice here, that as we come up here through this upper section, there's a lot of flat lines in it. It's not particularly great as a shear log. Back in those days, we're just on the cusp of digital logs, but they weren't too sophisticated in terms of recording the shear velocity, which is a bit of a tricky measurement to make at that time. And in fact, what those of you who've watched the channel quite a bit, you'll know that one of the things I like to do is always normalize the gamma ray. It's always good to have a normalized gamma ray about the place, because then you can compare from well to well by formation, hole size, and you can make comparisons more easily. The environmental corrections on raw gamma ray logs can be dependent on hole size and all sorts of other mud additives and things. So therefore, it's good to normalize the gamma ray and have one about the place, because if it comes in useful, as I'll show you in a minute. The other thing we need to do is just identify the fluid zones here, and we knew from that time that the oil leg was here and floating on top of this water leg. So all the water bearing logs are down here, the low resistivity rocks here, some tighter rocks down here because the porosity is a bit poorer, so therefore it's more difficult for the current to flow. So it gets resistive because it's tighter rock. But here you can see the resistivity is raised here in the oil leg. And let's have a zoom into that oil leg. And one of the first things to note, the first observation that I make when I look at the oil leg was, it's not very good, is it? You know, because if you go back to my Petrophysics for Dummies scene, we like to see this nice yellow sand down here that the geologists can shade in yellow. But there's a lot of this green stuff, which I've shaded in as shaly rock sort of stuff. So that is here. The gamma ray is quite high as well. This normalized gamma ray is quite high. the resistivity is high. Normally the shales are quite low resistivity, and this is definitely oil in here, and we knew from the cuttings as we drilled it that it was oil bearing, but it just doesn't look very nice from a density neutron crossover point of view. And here I've put a caliper in this far hole section, so it doesn't look very good. So one of the things I noticed as well is that this hole here, you see the caliper is washed out, and this affects the logs, tends to make them washed out. A bigger hole size, the tools can't read formation very easily because there's lots of mud in the way, and we lose contact with the borehole wall as the hole gets bigger. So let's see if we can tidy these logs up a little bit. So I've already mentioned that this sonic log, this shear log, was a bit poor, and you'll see here I've put a pseudo shear in its place, and let's see how I derive that. Let's have a quick log repair, see if we can tidy these logs up. So there was this poor shear sonic in there. You know, this was the log recorded at the well site. I think even in those days we would have sent it back to Schlumberger into their computer center, the FLIC, as it was called then, the Field Log Interpretation Center. Atlas's was called the LAC, the LAC, the FLIC and the LAC, onshore processing to make up excuses, to reprocess logs from the offshore environment. But this time I've just downloaded this data from the website, the NSTA government website, and I think they have only got the well site logs available, so this is pretty scrappy. So I wanted to tidy this up a little bit. So basically I derive a pseudo shear from the compressional. You saw earlier on where it was working, where both logs were working down below in the good rock. I came up with a relationship. Shear is some function of 1.8 times the sonic plus take away minus 3.2552. So that's the compressional sonic, and it predicts the shear velocity. It's not too bad. It's good enough for government work, as they say. And the other issue is you'll see that in the washouts here, the density seems to be washing out. So here is a pseudo density log. My software has this thing called multivariate regression, where you shove a bunch of curves into a black box, and then you say, okay, can you predict row B, the density, for me? So over the good hole, I exclude the bad hole from the training data set. So I say, what relationship with a bit of gamma ray, a bit of resistivity, a bit of neutron, and some sonic, can you predict what the density is? And it comes up with some regression coefficients and says, yeah, this is what I predict the density. And you can see over the good hole, the red kind of overlays the density pretty well, actually, pretty much predicts the density where the hole is good. So therefore that gives you confidence that the relationship is reasonable, and then you predict the density over the poor bit. So you've got to be a bit careful. Obviously, if you use the neutron, might also be a little bit affected by washout. The sonic is generally less affected by washout because it takes the quickest path from transmitter to receiver. So it's okay. So you can basically predict a relationship here. So if we say, where's the bad hole? Well, I shaded in everything in the caliper that's over 10 inches. The hole was originally drilled at 8.5 inch hole, so 10 inches is washed out 2 inches over, which is quite unusual actually in oil-based mud. Normally oil-based mud hole conditions are very good and you don't have this issue. So I don't know, it was an early well, maybe drillers didn't quite get the geometric, the weight right or whatever, and we drilled it a bit tentatively maybe as we got on, and you'll see a later well later which are much better hole conditions. But anyway, so 10 inches, that looks a bit harsh. Let's take it to 10.5 there, you see. So 10.5, I'm going to say that's where the main washouts are, and everything else is pretty smooth in between there. So what I do is I say over the 10.5 inch hole sections, let's splice in the density. So if I toggle back here, you'll see there's the pseudo density, and splice in the pseudo density over the bad hole. And if we kind of, tell you what, let's zoom in a little bit to this upper bit here. I'm not too worried about the shales. Being a petrophysicist, I'm not too fussed about them. Geologists and geophysicists can be, and drillers can be as well. So here's the original density. You see this washout with a caliper. This thing here is called the PEF, the PEF. I don't think I covered that on my Petrophysics for Dummies course, but it's largely affected by washout as well, where you get mud build up, barite in the mud. It affects it. So you can see this is where the hole is washed out. And if I splice in the good density, or the pseudo density, shall we say, you see that it does a reasonable job. This makes it look sensible, shaly rock, and there's some improvement. Let me just, I've got to go all the way through this now. There's some improvement in the reservoir interval, the zone of interest. This NRD 0 zone is quite washed out here, and you can see that the density is out to lunch, as it were, as we say, and it's marginally better here with the pseudo log. Anyway, done my best to tidy it up as best I can. Okay, so what do we need to do next? Well, we need to prepare to do a CPI. The CPI is the computer processed interpretation. It's an old nomenclature for it back in the day when using a computer was a bit novel. So many people still call them CPIs. I think when I was at Shell in Oman, we used to call them RDLs, Reservoir Description Logs. But pretty much most of the industry would know that if you said it's a CPI, that's the interpretation, computer processed interpretation. So what I've done here is I've just added some empty tracks into which to put the interpretation, and we run a conventional interpretation, computer processed interpretation. And here is the oil leg and the water leg. Here is a V shale, the clay content of the reservoir, if you like, with an effective porosity. Here's a total porosity in red. If you're a shell person, you like total porosity, and so that's the total amount of holes in the system, and it includes the holes in the shales as well, which hold water. The shales at this particular age do have quite a bit of water in them. Some of the older, deeper shales get the water driven out of them, and they don't have much porosity. But that shale porosity isn't much use for storing hydrocarbons, and it's difficult. Hydrocarbons can't get into the shale. So many people would call that non-effective porosity. So the effective porosity, if you like, is you take away that stuff that you associate with the clays, the shales, and you say, right, this is the effective porosity that's available for hydrocarbon storage, and it's the one that reservoir engineers are actually interested in when they do their simulations. But the whole phi T for total and the phi effective, phi E, that's probably a subject for another video, and much discussion and argument between petrophysicists or whatever. But that's what this yellow orangey curve is. The cleaner the curve, I've shaded it in slightly lighter yellow. And here is the saturation, and I've just realized as we speak that I've shaded this in red. Now normally most of the industry would shade oil in green and gas in red, and I've done it the wrong way around this time. It's actually the way that Shell does it, so I guess it's kind of appropriate that after they bought Enterprise Oil, and so I imagine that the Shell guys in Nelson plotted all in red anyway, so maybe it's a bit of foresight on my part. But I do apologise to the rest of the world and the rest of the industry that this is shaded in the wrong colour, as far as I'm concerned. And then in the last track we've got permeability, which again you can go back to the Petrophysics for Dummies course, learn all about permeability. Okay, so one of the things that the results of this is that within this oil leg as a whole, I'm calculating we've got 40 foot of 40 foot of net reservoir, so sand if you like. So in this 300 foot oil column, we've only got 40 foot of sand. That's not too good. That's 15% net to gross. I seem to recall at the time it was kind of deliberate that we drilled the first well into the interchannel area. If you look at Nelson, and I don't have a map to hand, it kind of has two kind of channel fairways, we call them, which is lots of sandy bits. And then in the middle, there's a kind of like what we call an interchannel area. And in fact, that's where the very first, I think it was the very first well in the North Sea, northern North Sea well, 2211-1. There's a dispute about which was the very first oil well, but I think it was 1967. And the well actually did test hydrocarbons, but it wasn't, but in those days, it wasn't enough. And I guess it was potentially the very first hydrocarbon discovery in the northern North Sea. But then I think Montrose and Arbroath were drilled short time afterwards. But so I think we would say that it was a deliberate idea to drill this first well into the middle, between the channels, to work out how much sand was there, because it's obviously one of the big uncertainties when you do a field development. You drill up the easy wells and you look at wells and you try and work out how much oil is in the reservoir, but there was a big unknown about this poor reservoir area in the middle. So I think, as I recall, we did it deliberately. Anyway, I think that's what we told management. But overall, a bit of a disappointing well from an absolute reservoir point of view. So we've got 40 foot of net in the oil column as a whole. So what are we missing from this data set at the moment? Well, if we had a saturation height function, on Nelson we had a saturation height function. I don't know what they use these days, but back in the day it was a Tamiya-based pseudo capillary pressure curve. So this is like the amount of oil that normal Nelson rock at this elevation would contain. So all of this red stuff, all this oil should really be reaching this line if it was a normal Nelson well. So you can see that there's not as much oil in there as we would have hoped to from a saturation height function. But that's the typical Nelson saturation height relationship. So one of the things I wanted to double check is my petrophysical parameters. So I kind of like sometimes plot the constants that I've used. So these are the input constants that I've used in my analysis. Obviously, sometimes you make a typo, you type in something wrong. So I think sometimes it's good practice just to sort of, here's the density shale density, row shale down this line, this brown one here, and this dashed one is the neutron shale line. So I want to make sure that I pick the points that makes that 100% shale, and then everything in between is scaled appropriately. So I just double check. I just check that this is the shale sonic response as well. That all looks kind of reasonable. The parameters that I've chosen seem to be okay. I haven't made a mistake. This is just genuinely a pretty poor reservoir. So the other thing, as you may have just seen, is that we have core data, of course. We did cut the core. As I've mentioned before, it comes in a bit later, oftentimes, than when you do your first log analysis at the well site. And so this is the core data that we've got. And you can see here that this is the porosity data. And this is the water saturation specifically. And you can see actually the water saturation does agree with the saturation height function. So that's interesting. So that suggests that those particular core plugs are as good quality as we would expect from the rest of Nelson Reservoir. Similarly, the porosity ties in pretty well with the sonic porosity, the total sonic porosity, and not too well with my phi E interpretation. So all the Shell guys would say, well, what do you expect? But nevertheless, the core is kind of hinting that there's something there. And here's some core photographs here. They're a bit compressed at this scale. This is the white light photographs, and I'll show you these in a minute. And this is the photographs taken under UV, ultraviolet light. Under ultraviolet light, oil fluoresces, and you can see here this white stuff here looks white at this scale. This is the hydrocarbon bearing sands, and actually, if you look through there at this scale, you can see there are some sands in here that appear to be more than this. This is the net flag from my log analysis, net pay flag from my log analysis, you can see where I'm evaluating sandstone or net reservoir, and there seems to be a little bit more in the core photographs, so that's interesting. And this is a flag I've made from the core photographs. This brown and yellow flag. I've gone down and I've had a look at the core, and I've decided this is the net flag. And basically, what I want to do is I want to show you now how I did that. Let me go to the core. Of course, from Petrophysics for Dummies, you've seen what the coring is all about. We cut the rock down in our borehole, and the core goes up the middle of the core, and we recover it to surface, break it out on the drill floor, and then lay it out on tables, and the geologists can have a look at it, and we can make some measurements, ship it back to the lab, and make some plug measurements and take some photographs of it. So what I'd like to do now is go back to my former self, my past self, and show you how I did it at the time. So if we go back to our past self, there we go. Over to you. Okay, thank you very much, future self. I'll take it from here. I'll just take you through a quick session of how I created that digital net core flag, if you like, and what I did to cut up the core photographs. I used a bit of software called Core Chopper. Now, I'm not sponsored by Core Chopper. The guys at Logicom, E&P, who write the software, kindly let me use and abuse it in return for my efforts in helping them debug it and make a few awkward suggestions to them. But nevertheless, I found it quite useful just to be able to chop up some core photographs and load them into digital areas where I can make digital logs out of them. So this is how I came up with that core flag. So I take the core photographs, which I've downloaded from the NSTA website. If I can just find my cursor, here we go. So here's the core photographs, and here is the usual white light and UV pages, which I've saved to JPEG files or whatever. You can see the white light photographs are interesting. The UV ones are less interesting. So under ultraviolet light, the oil glows and fluoresces, and it doesn't start to get interesting till down around about here on page 110 of the core analysis report. And you can see that under UV light, so that's the white light image, and then the UV light fluoresces, and you can start to see some of these thin beds. If I click to every other one here, here's that thin bed stuff. Obviously, this is routine. We take core photograph plates. The core analysis laboratory puts them into trays, and depending on the hole size, depending on the width of the core, depends on how much you can fit on an individual plate. So this particular one is fairly typical for the Nelson wells. It's 8.5-inch core, and they could fit 6 boxes of 3 foot, so 18 foot per plate. If it's large core in 12.25-inch hole, you obviously sometimes you get 4 boxes, and if it's 6-inch core, tiny little 2-inch core, you can fit more on. But basically, you load these core plates up into the software. You load the images. You set the units, feet or meters, and then you basically put the rectangles on. You say I want 6 rectangles, and then apply that to all the photographs. So here you can see here it loads up all the photographs in one session, and you type in basically the top depth and bottom depth of each image, and you say how many core boxes you want, and it's 3-foot compartments, and it basically populates this depth table for you, this core table, and you can basically adjust. What are basically going on there? You can adjust the top depths and bottom depths as you see fit, and I'm sure that the guys at Logicom will be able to help you out. One of the things that we did, as I recall, was that we flagged the core here. For green was where we were pretty confident the core was continuous. Yellow or amber was potentially, there could be some missing core or little breaks in it, and the red was oftentimes rubble. I think if there's a better example here, for example, here's the core is kind of rubbleized, and therefore if you needed to break the core or make breaks when you're depth shifting it to logs, obviously you've got solid rock, so you don't really want to stretch and squeeze it, but you have opportunities to sort of move sections of it about in a section shift, if you like, and sometimes you're looking for areas where you can break the core digitally and depth shift it to your logs. And so the idea behind this was to be able to get some sort of idea of where breaks might allow. So what I want to do is I basically take these boxes, these blue boxes, and you can move them around and shift them on the core. It's a bit slow at the moment while I'm doing the video. It seems to slow the screen down, and you can adjust the core sizes or individual boxes or all together and stuff like that. And basically you set it up to have a look at you set it up to save it with these boxes, and you can adjust the depths. And if we just process the current image, it just takes this first image and goes away and adds in, here you go, it adds in these single plugs here. And you'll notice that when it's cut, it basically puts the top depth and bottom depth on each image name, and you can go through and check that it's doing it the right way around. Let's have a look at a bit more of an interesting one here. Yeah, let's go to one here with preserved samples here. So you can see I've tweaked this box, and to be honest with you, it probably took me an hour to go through this and mess about and tweak it a little bit. You can adjust the images, you can rotate them slightly if your photographs aren't quite as well behaved. So let's process this current image. You can do all that and then process them all at the end, but and often that's what I do, but oftentimes it's better to just to keep check on it, sort of stuff. So which one's this? 9038. So that's the new image here. So you can see, just to check that I've got the nice little bit of yellow stuff down the edges, red there, and all of that kind of good stuff, just to check that the images are processed. Now, obviously it puts the top depth and bottom depth, and because the log analysis software I use is also written by Logicom, this basically loads up straight into my log analysis software. But even if you don't have log analysis software to load it up into, and you're just a jobbing geologist or whatever, one of the things you can do is to load it up into Excel. So here is my routine core analysis spreadsheet, and I use the Excel conditional formatting just to highlight some issues here. So I use these box conditional formatting. So this is porosities in green. This is the gas expansion porosity, and in this case a fluid summation porosity, and these are permeabilities, the air permeability and the Klinkenberg corrected permeability. And also I've made an estimate of net sand or from the core photographs. Let me show you that. So what I did is oftentimes I take the core gamma rays or the mini perm data, and then I use a lookup. I use a lookup to sort of interpolate it onto the routine core data. But what I've done here is I've taken the core photographs that I've extracted, and I've worked out, I've decided I'm going to work at digital foot level. So this is 0.1 of a foot. So 10 rows is 1 foot. So 30 rows is going to be 3 foot. And then I've imported the core image, and I click on an image there, and I worked out that if I do the plot format, it's 15.52 centimeters long. It'll make the images 15.5 centimeters long, and then that will be roughly 3 foot on this scale. And basically you can load this up into Excel. And what I've done is I've gone down and I've made an estimate. It's still qualitative, I guess, because it's my interpretation. But, and I can go in and tweak it. So I've decided I'm going to call that one net. And then I'm going to say, well, I'm going to call this 0.5, because
there's lots of stuff in here. It's an interpretation. So some of them I've gone 0.5. I think at some point I might have even put a few 0.25s in there or whatever. But basically, I'm kind of looking down this photograph and I'm making an interpretation where my net sand is, and I can look at the UV and the white light together. In fact, probably easier if I just show you a print preview of it actually. So I can make this core log, which you can print out. What is it? 54 pages long. But you can see this is an interpretation. I've gone down here and I've made an estimate of sand. And a geologist, a better qualified geologist than I, may also be able to do the same thing. So then, obviously, because it's in Excel, I'm able to then export it as a digital file, depth from and to, 0.1 of a foot sampling, and load it up into my software, which is what you see, which is what Future Self sees in these digital logs. The only other thing to mention, the little quick tip that I use, is obviously it's quite tricky. That's okay on the white light one, but the UV ones are a little bit trickier. But what I do is I save this core chopping session, if you like, as a session, and then I go and edit the session file, which is just a text file, and I global replace all my white light JPEGs with UV JPEGs, and then I load it up. I load the UV session up here, and even though it's a bit tricky to work out where the boxes are, you'll see the boxes on there, and obviously when you can zoom in at a bit better scale, you know, so you can see the outline, and you can come in and you can tweak the boxes there in the UV session. As I say, it gets you started. It's quite useful. I mean, obviously some of the UVs, particularly down in the oil legs, are a little bit easier to work with, but once you've saved the session, you save the boxes and all that kind of stuff, and it helps you do the UV ones a lot easier. So with that, I kind of load up my digital log into my log analysis software, and then I can plot it on those plots that you see Future Self using. Hopefully that's interesting. I'll leave a link down to this core chopper software, and you can, if it takes your interest, I'm sure Joe and Kenny will give you a great deal on it. All right, thanks a lot, Future Self. Good luck with it all. Hope you enjoy the rest of the presentation. Cheers. Right, thank you. Thank you very much for that. Okay, so that's where we got the core log from, and so that's where we derived this core flagging technique from. Okay, and I can, as I say, because it was in Excel, I was able to import it into my log analysis software and see if we can match it. So here is the core count, the net sand count from the core, and what I've done is I've sort of split it up into core intervals. This is core 1 and 2, which goes above here, and this core 3, because these are significant gaps, and core 4 to 9, that's continuous as well. So I've taken those chord intervals and I've used this somewhat subjective flag to calculate how much net sand there is, and within this chord interval I can see 167 foot of sand, net sand in there. Now, taking our conventional log analysis, which is these net sand flags here, and plotting them, calculating it over exactly the same intervals, give or take a bit of depth shifting, so exactly the same logged intervals, I'm only calculating 28 foot of net. So in the core I can see 167 foot of net, and in the core I can only see 27 foot of net. So what's going on then? What's the issue? Well, as I hinted at before, the issue is resolution. Now typically we make log measurements every 6 inches down the wellbore. This is the lovely Maggie Murison from Trax International. It's a really good course I can recommend if you do it. It's the Reservoir modelling course up in Elgin in the northeast of Scotland. And she's holding up here this equivalent log of the section logged every 6 inches down the well. It kind of looks like 12 inches to me, but it's supposed to be 6-inch log sampling down the well, so that's the depth sampling. And there are various degrees of depths of investigation here in this bedsheet here that Mark Bentley is holding up. And you can see here, if this was the borehole here, this is the zone of investigation of the density tool. And coming out here towards Mark is the depth of investigation of a resistivity tool. So you're averaging big volumes in the resistivity space, and even quite big volumes in the density logging space as well, and in the gamma ray as well. You can see that there's a lot of geology, a lot of fine scale geology is being averaged into each point log measurement. So what we need to do is try and see if we can deconvolve it. Can we get to understanding the thin beds and the stuff going on between the log measurements? So to do that, I'm using a technique by a guy called Richard Bateman. And I guess at the time, this was his 1990 paper, and we are 1991 for Nelson, so we were at the cutting edge at that time. Obviously, looking back on it now, obviously it looks a little bit dated, although Richard, fair play to him, he's kind of aged quite well. He's just retired. I think he's retired in somewhere in the States. Aren't we all retired these days, I guess? He seems to have weathered a little bit better than me. I maybe have a little bit more hair than him, but he's looking remarkably healthier, actually. Anyway, so Mr. Bateman, Richard Bateman, I'll just call him Bateman if I can. He came up with this adaptive filtering technique. It's well worth a read, the paper, actually. Richard has a classical education from Oxford. He uses some very big words, but nevertheless they're still quite readable. He's come up with this sort of filtering technique, and we modified it with the use of some normalization processes and also standardization, and I'll talk about that when we come to go through the presentation. So this is the reference down here: thin bed evaluation with conventional log suites. And this is really the crux of this whole presentation. I've been using it ever since, on and off. I've employed it in Oman, in carbonates, and in Gabon, in the lacustrine sequence, very thin-bedded lacustrine sequence. That reservoir development didn't go as well. Anyway, that's another story, perhaps for another time. So what Bateman said was that if you imagine you have 6 foot of 50% V shale in a simplified model. So this is 6 foot of rock and it's 50% V shale. Well, actually, you could consider that to be 3 1-foot sands and 3 1-foot shales, and that would add up to exactly the same thing. If you accumulate the sand from the top to the bottom, overall it's still 50% shale, and it's still 50% shale in the discrete version as well. And so these interpretations are volumetrically balanced. So what Bateman came up with, he said, well, okay, what if we log a gamma ray? So let's put a squiggly gamma ray. So it's not particularly well drawn. This is a bit diagrammatic. So we log a gamma ray through our rock section, and then we filter that log gamma ray, and then we take the difference between the filter and the log signature. And in the shaly layer, obviously we get a positive deflection because we're taking the filter away from the filter. Take the original away, leaves a positive shaly wiggliness, if you like, and then the gamma ray minus a bigger sandy squiggle gives you a negative squiggle. It's all about the squiggles, basically. So in essence, you're kind of extracting a curve activity curve, which basically says, okay, this wants to be a sandy wiggle, and this wants to be a shaly wiggle, and we can use that higher resolution to say, okay, even though our baseline interpretation, a standard V shale, would scale the logs from 0 to 1, if you like, we can look at the degree of wiggliness and we can say, okay, well, that's a shale tendency, and that's a gamma ray, and that's a sand tendency. And we can use that perhaps with a gain and offset to scale it such that we can model both ways and make sure that we keep our volumes balanced throughout. I'm going to show you in a little bit more detail with some examples from Nelson about how we actually went away and did this. So this thin bed methodology, let's open up our thin bed analysis windows, if you like. So here I've got a conventional gamma ray sand shale interpretation, and remember we've got to find 167 foot of net from the core, which is this core flag here, which, remember, I went down and interpreted from Excel and then loaded it into here. So let's choose our shale indicator, and I've just chosen the normalized gamma ray, my favorite normalized gamma ray, and I'm shading it in here to above 50, so that's the shaley bit. So conventionally this would be all the shale, so which is why not much of it makes it below the sand cutoff. This V shale here, by the way, is calculated with a combination of dense neutron, the lowest of the dense neutron, and the gamma rays. So the dense neutron measurement here is actually seeing sand here, whereas this gamma ray is still above 50%, so that wouldn't see it. So anyway, I digress. So what we do is we take our, remember, we do our first filter, a long filter, and what I've done is I've said, okay, so in the stuff that's over 50%, let's call that shale background, and in the stuff that's less than 50% V shale, let's call that the sand background. So what this methodology is going to do is going to look for thin sands within the shale background, and it's going to look for thin shales within the sand background. So if we take the short filter, which is a 2 foot filter, which kind of represents the sensitive measurement volume of, say, a gamma ray, pretty much affected by the rock 2 foot, a window 2 foot, either 1 foot either side of the measurement, if you like. So that's like the natural tool resolution. And if we take the long filter from the short filter, we get this sort of, here you see this, the brown is the shale wiggliness, and the yellow is the sand tendency. So if we take the difference between the two, obviously on average it'll be around about 0. So these are the sand wiggles and the shale wiggles. Okay, and so what we need to do is kind of scale them appropriately. One of the things we can do is standardize this curve. So obviously if we standardize it, that kind of puts some statistical noise or a statistical rigor into the system. Basically, what we're doing with a standardized approach is we're taking the difference and we're taking the average of it. So this is the reading minus the average reading. So that's the variance, if you like, the residual plus or minus to the average. And then if we divide that by the standard deviation, we're basically scaling this wiggliness in standard deviation units. So depending on the variance of the curve, we're kind of saying, well, if it's a noisy curve, it'll have a high standard deviation. And so the number of standard deviations will be appropriate for that particular curve in that particular environment. So if you had a particularly noisy one, well, then it would be noisy, and it would kind of like normalize the wiggliness, but it expresses it in terms of standard deviation. And if we can do the same, so therefore basically anything above, typically in error analysis, you would say that anything within one standard deviation is kind of within the noise. So you wouldn't necessarily put great store in that. You'd want to sort of say, okay, it's not significant unless it's excess of one standard deviation. So I've just shaded that in here, the one standard deviation. Actually, this is a slightly scaled curve. So anyway, in point of principle, that's the idea, that these are statistically significant because they're above the level of background noise. Okay, and we can do a similar thing for the V shale curve itself. We can express its variance in terms of standard numbers of standard deviations. It kind of makes the units compatible, and that's quite handy when you get to do statistical processing. Every bit of degree of signal, if you like, in the curve is expressed in terms of the number of standard deviations of that curve. And if you notice here that I've just displayed them both on -4 to +4 standard deviations, and there's a kind of a crossover there. The clean sand and the shales kind of cross over like a pseudo density neutron, if you like. More of which later. First off, I'm just going to use the absolute standard deviations as shaded in here by the yellow squiggles and the brown squiggles, and then we can compare that to the core flag. So that's where the yellow sand is, and you can see it's quite. So this is our analysis. We've got a little bit more sand than our conventional core analysis here. A little bit more different net flag. And does it tie in better with the core? Not particularly, but you can see some scope there. Let's plug this into the interpretation anyway. Oh, let's do our V shale check first. So here you can see the V shale check. Everything's sticking pretty much around about 0. This methodology is not adding in too much sand, and not adding in too much shale. So it's pretty neutral, volumetrically balanced. So this is what Richard would like, I guess. This is the idea. Let's not add in too much sand. Let's not add in too much shale. It's volumetrically balanced. So anyway, let's use this particular V shale indicator to set up our binary V shale and then run our analysis. Oh yes, remember, so over this interval, before we do that, the conventional log analysis, remember we only had 28 foot of net in here, didn't we? Remember when we looked at the conventional log analysis over the chord interval, we only had 28 foot of net. If we use this binary V shale curve, we can use that in our analysis now, and the net increases to 80 foot. So we are getting there. We've nearly tripled the amount of net we've got, and you can see. So now the interpretation uses that V shale, that binary V shale indicator, and in that sand, I'm going to use this sonic total porosity. This is now clean sand, 100% clean sand. And I'm going to pick up the total porosity as calibrated to the core data. So that looks okay, and that's as far as we get. So we get 80 foot, but we're still nowhere near the 170 foot that we need. So as I say, this one I cheated slightly already. I've amplified this. I've multiplied this scaled curve by 1.5. If I multiply it by 2. Then I get a bit more sand. Oh, actually, it drops down a little bit, interestingly. So if I go, this is 1. In this particular section, it looks like it's got a little bit more sand in this particular window. It looks like it's increasing the thickness, as you might expect. But overall, elsewhere, it's calculated. It's actually dropped slightly. And it's important to remember, probably, when we're scaling this difference curve, you're adding in thin sands for sure, but you're probably adding in thin shales as well. So you're adding in thin shales to the thicker sands, and you're adding in thin sands to the thicker shales. Stop and think about that for a while. Have a cup of coffee. You'll understand what I mean, hopefully. So in this particular case, the first time around, although it looks a bit thicker here, it looks like it's actually adding, taking away sand. over the interval as a whole. So let's go to 3. Now we get a bit more increase. So if we've amplified this up to 3, and we're up to 90 foot of net, so we're back to where we started. And again, now potentially, are we seeing a better match to the core, the core flag in here? Potentially. Let's amplify this V shale. So this standardized V shale is, let's amplify it, let's double it. You see, so it's now, I'm plotting it from -2 to 2. Did you see what happened there? Just let me double that, you see. So I'm increasing, I'm just turning up the sensitivity as a V shale. And let's see if I use, what happens if I use this total crossover now. If I put aside this one standard deviation cutoff statistical significance, because I'm already multiplying, you can see I'm starting to add in a little bit more shale than my conventional log analysis. So let's use the crossover, the total crossover now. It's a bit of a drastic change, isn't it? So now I'm going to say everything that's total crossover is the sand, and my balance curve goes out the window. I'm up to 123 foot of net by now, so I've put an extra 100 foot of net in. I'm still short of what I picked in the core, but nevertheless you can see that, okay, this wants to be a shale, this wants to be a sand, so I'm gonna say, okay, forget the statistical meaning of it, let's just calibrate it to core. How high can we go, sort of stuff. So that's more dramatic, isn't it? I mean, in a way you can see there's a better match to the core plugs. There is, of course, a risk that obviously when you've got two noisy things and you try and correlate them, there are a number of correlations, and so you can fool yourself into thinking, oh yeah, that's right, because there's just so much noise in the system. So I'm not going to hold out too much hope that this is actually right, but it does seem to match a little bit better to the core and the core plug data. So actually, if we kind of zoom out to the whole log interval, you see how dramatic that looks now. So you can see, stepping back, that kind of looks okay-ish. There's probably still a little bit more sand in the core. Well, I can tell you there's 170 foot of sand in the core, and this method is only getting us up to 123. So this would be our final thin bed CPI. Now, one of the things is that the saturations are still not good because they're still suppressed. The resistivity is potentially suppressed. Now, using the saturation height function, that's the idea of saturation height functions, that if this resistivity is suppressed, because shale is a conductor and it has a lot more conductivity than oil-bearing sand has resistivity, if you like, in terms of conductivity modeling. And in fact, one of the things that Richard Bateman suggests in his paper is that you can do a simple, using your understanding of the formation resistivity factor, you can build a conductivity model for all the shales. If you build this earth model of the shales, you could put in the conductivity of the shales and the conductivity of your resistive sand layers, and then you could build and forward model a resistivity, and then take a logging response curve, filter over it, and see if you could recreate this resistivity profile, given that there's shoulder bed effects. So I haven't had time to do that this time around. Maybe next 35 years I'll get around to doing it, but that's something you could do. You could forward model it and see if you could work out what your R sand, resistivity of the sand, would be, and then calculate Archie. I will probably have a go at that after I publish this video. I mean, I was getting sidetracked by this Nelson stuff, so I thought I need to get this out, this video out. But anyway, so what I've done here anyway is I said, well, normal Nelson rock and this core data suggests that the saturation should be there. So in this thin sand, what I'm going to do is I'm just going to take the saturation height profile. So there you go. That would be my final first pass interpretation for this well. As I say, it is a better match to the core saturation. We could model the R sand and R shale with a conductivity model, and that's something I might do next time. And if it goes well, I'll put another video up. If it doesn't go well, you'll never hear of it again. Okay, so that will be our final interpretations. But let's just kind of compare back to where we started with our conventional log analysis. So 123 foot of net with our conventional CPI. What happened there? Oh yes. So let's go back. Yeah. So that's the conventional. Yeah, that's right. With the 27 foot of net. And that's the thin bed interpretation. You see, I think there's some scope for improvement there. I mean, that seems to be on the right track anyway, and maybe there's some tweaks we can do to improve things further. Now, yeah. Of course, I wouldn't want to leave you, so this is kind of the end of my presentation now-ish. Oh my golly gosh, it's been going on for quite a while. I'm not very good at getting these short, am I? So I wouldn't want to leave you with the idea that this is a typical Nelson well, because this is a typical Nelson well. This was N9. It was the very first well drilled from the platform. N1 was drilled before the platform was put in place. Actually, it was pre-drilled from the Dundee Kingsnorth, and this was N9 drilled from the platform, and this is more typical thicker sands in the channel axis area, and it's a lot better. But you can see the same saturation height function here. If I just toggle between the two, you can see that's what good Nelson rock looks like. Good permeabilities, and this is what poor Nelson rock looks like. But of course, to be consistent, we could do a thin bed analysis on here. You notice up here there's a little bit of abandonment facies up here, a little bit of thin beds going on, so we could look at that. But obviously, as I mentioned before, you do a thin beds, and you potentially put not only do you put sands into shales, you potentially put shales into sands. So this is exactly the same methodology before, using this crossover. You see, you put a lot of shales in there. Now, I haven't got around to core chopping the N9 data because I've downloaded it. I've probably got access to the photographs, and I probably will do that. If I get around to doing that resistivity modeling, I will do some more core chopping and calibrate. Are all these shales real? It seems a bit unlikely to me, so you could play some sensitivity games with this sensitivity. So I'm going back to some other methodologies, looking at some sensitivities here. Here I'm overestimating the amount of sand with this V shale check, and here I'm underestimating the shale. Sorry, other way around. but here it would be interesting. One thing to know: the reason I put this thin bed shale on the resistivity curve is that, you know, from a conventional point of view, you'd like to think, you may think this is a large Chanco sand, really big homogeneous pile of sand. But when you plot it out here, you can see that there's perhaps some agreement this is from a gamma ray with the resistivity profile. So there are some things going on there that maybe they're real. So the gamma ray is completely independent from the deep reading resistivity. So there may be some thin laminae going on, some thin shales. Now, I don't know. I stopped working on Nelson in 1995, 96. So I don't know later on in field life whether RFTs came along or if they made pressure measurements. Probably not, actually. And whether you can see little laminae and little shale breaks with effective on the RFT data, the pressure data. Were these things acting as baffles? Maybe some of them had little preferential sweep as the water flooded over certain shale barriers. I don't know. it would be interesting to talk to a reservoir engineer about what they think the effective KV, KH is. Some of the later wells, which are all released now, I may well go, out of interest, go back and look at some of the later wells and see if I could see any evidence for compartmentalization or little baffles in the system. But to be consistent, as I say, you can adopt the same approach. It's just a question of, can we come up with some consistent amplification parameters for this kind of methodology, such that it would be sensible to use them field wide. Okay, so I think that's pretty much all I had. Hopefully it's given you some ideas of things that you can do, some techniques. Next time you have a thin bed problem or a thin bed issue, maybe have a go at this, and then, as I say, because it's still quantitative, it's just a question of what numbers you use to tweak, to adjust to taste. Hopefully you found that useful. I've certainly enjoyed working it. I was going to put the YouTube video out last week, and then I kind of looked at the N9 data and I kind of get carried away, reliving the good old days, as it were. So hopefully you've enjoyed that, and I know I've drifted on again far too long, but in for a penny, in for a pound. Okay, thanks a lot for your attention, and hopefully see you next time. Hopefully you think it's worth a subscribe at least, and I look forward to seeing some of your comments in the remarks section. Thanks a lot. Cheers.